On the board behind me are a couple of arithmetic sequences. 1, 2, 3, 4, 5, 3, 5, 7, 9. They're all sequences of numbers where you start at a particular place, 1 or 3, and you get to the next number by doing the same thing, by adding the same thing each time. Adding a 1 in this case, adding a 2 in this case. Now, with a little mathematical wizardry, I'm going to turn this arithmetic sequence into an arithmetic series. When we add up the terms of a sequence, we get a series. And, by the way, if you're trying to remember which one's the sequence and which one's the series, just remember that Q comes before SER in the alphabet, and you have to have a sequence before you can add them up and get a series. So that's how you can tell them apart. Anyway, I'm going to show you a formula for adding up an arithmetic series. Now, for series as small as these, we wouldn't bother, we just add them up. But if you were adding up a big series where they were separated by big numbers, starting at 2,567 and adding 24 to get to the next term, you wouldn't want to have to do all that. So there is a formula, but before I tell it to you, I'm going to tell you a story that goes with it. This story concerns Carl Friedrich Gauss, who was known as the Prince of Mathematicians, one of the most brilliant minds this world has ever known. When he was 10 years old, he was going to school in Germany. That's where he was born. And his school was typical school of that time. Not a great school, not a terrible school, but the teachers were allowed to beat the kids in those days. So his teacher, Herr Büttner, carried a switch at all times. And if the student gave the wrong answer, or if the student had the wrong expression on their face, or if the teacher was just in a bad mood that morning, well, Herr Büttner, reports vary as to whether he was a sadistic brute or just not caring very much. But apparently he liked to give himself a break in the middle of the day by setting the kids a meaningless task. Add up all the numbers between 1 and 100, or between 5 and 300 separated by 4. Well, what is he doing but telling the kids to add up all the terms of an arithmetic series? Young Gauss, at age 10, after 1 minute, walked up to the front of the class with his little slate board on which the students wrote in those days, and he slapped it down on the teacher's desk and said, "Liegt sie," which means "there it lies," and walked back and sat at his desk. I can just imagine Herr Büttner. "Oh, your posterior is going to be so sore, young man." Well, over the course of the next hour, one by one, the rest of the students finished up the task and tiptoed up to the front of the room and set their slate boards down. And when the last student had finished, Herr Büttner picked up the boards. Wrong. Wrong. Dummkopf. Wrong, wrong, wrong. And then he got to the very bottom of the stack. This is right. How did Gauss do it at age 10? He realized that if you take the terms of the series and write them backwards, right in that lovely space where I demonstrated sequence versus series, looks like this. 5, 4, 3, 2, 1. I mean, he did this with a much bigger set of numbers. I'm showing you on simpler numbers, but the principle is the same. 1 and 5 is 6, 2 and 4 is 6, 3 and 3 is 6, 4 and 2, whoops, 6 there, 6, 6. That's a 6. Now, if you add up all those 6s, but you don't even have to add them, multiply 6 by however many terms there were. There's 5 terms there. 5 times 6, that's 30. Now, the sum of this series, 1 plus 2 plus 3 plus 4 plus 5, is actually 15, but that makes perfect sense because we added the numbers all twice. So we should get a 30. So as long as we divide our answer by 2, there it is. But does it work on any series of numbers or just on those? Well, let's try it on this one. 9, 7, 5, 3. 9, 10, 11, 12. 7 plus 5 is also 12. We already did 7 plus 5, 9 plus 3. 4 12s, that's 48. Divide by 2 and we get 24, which, if you want to add up 9 and 7 makes 16, 5 makes 21, 3 makes 24. Works again. But does that prove that it will always work? No, I'm afraid it doesn't. Because there might have been something special about the numbers that we chose to start with. There might have been something special about how many terms we had. A mathematical proof tries to eliminate anything that depends on specific numbers and show that what we're doing will work in every possible case. Don't be intimidated by the board. We are embarking on a mathematical proof. You know that part of the math textbook that if you read the textbook at all, you get to the beginning of it and your guys just go, that was helpful. Doesn't have to be intimidating. We're going to go over a mathematical proof and you'll be amazed at how easily you follow it. So what we've done is I've written out a generic series. I'm calling the first term A1. Could be a 3, but it could also be anything. So we've eliminated anything that might be special about having started with a 3. The difference between each term I'm just calling D. So the next term is the first term plus the common difference. Thus, we've eliminated any special circumstances arising from a common difference of 1 or 2 or any particular number. So here's an example. The next term would be 5 because that's the first term plus the common difference of 2. And then the next term is the first term plus the common difference of 4 and so on. And then starting from the other end, I'm calling the last term A sub n for the nth term, n meaning there could be any number of terms, so we've eliminated anything special arising from there being a specific number of terms. So let's say we're going to 17. Then the term before it would be 15, which is 17 minus the common difference, A sub n minus d. And before that would be A sub n minus 2d, and so on. And this little ellipsis in the middle means there could be any number of terms in between them. So, as generic as it gets, and underneath I have written the same series backwards. Let's see what happens when we add them up. So, A1 plus AN, that's first plus last, just like we thought it would be. Now, A1 plus D and should be a 1, sorry there, minus D. A1 plus, oh no, I'm right. I was right the first time. I knew what I was doing. But the D's cancel out. Isn't that great? So all that's left is A1 plus AN. And here, A1 plus AN, the 2D's plus 2D minus 2D. They cancel out. And so once again, we just have first plus last. No matter what the difference is, no matter what the first and what the last are, these cancel out here. Plus D, minus D, all cancel out. And in every case, all that's left is first plus last, first plus last, first plus last. And how many of them do we have? Exactly as many as there are terms. In other words, there are n of them. So if we just take first plus last and multiply it by n, and then remember to divide by 2, we have a formula that we have now proven mathematically has to work. And so we now are allowed to use this formula. S sub n, the sum of n terms, is equal to the number of terms times first plus last divided by 2. And as for Carl Friedrich Gauss at age 10, well, Herr Büttner did not thrash him within an inch of his life for being a smart aleck. Instead, Büttner, a more subdued and quiet man, went and with his own money bought a mathematics book and tried to really teach young Gauss Within a month, Gauss had mastered everything that was in the book. So Büttner found him a better teacher, his own assistant, in fact, and the assistant introduced young Gauss to the Duke of Brunswick, the area where he lived. The Duke paid for the young genius to go to college, and Carl Friedrich Gauss went on to become one of the greatest mathematicians of all time. In fact, I'll leave you with this thought. His mother, who had supported him against his brutish father, who had tried to keep him back at every opportunity, she asked a mathematician, "Is my little Carl, is he any good? Will he ever amount to anything?" And the mathematician said, "Only the greatest mathematician in all of Europe." And his mother